Hello everyone and welcome to this video guide. Today I decided to make a video to present my work on research, on a grid research, planetary grid research. So I've been working on this for months now in the back end, so I haven't been much posting articles or anything online, but much likely working on the back end, building my pipeline, a lot of mathematics and coding set in place to be able to come to those results today. So I've decided to present the work and go through a small video, a small presentation of what we're seeing here. Here is an EA lattice, a structure from 8-dimensional mathematics projected into the Earth surface at this statistically optimal orientation. So I had to find first the optimal orientation of the grid, of the EA lattice against a data set of 160 circuit sites. And out of 6,720 possible ages, 367 pass within 11 kilometers of at least one sacred or energetically significant sites. So they are not cherry picked. It's not something I've actually built it through visual, but it's the statistic who led to those results. And the tolerance of 0.1 degrees, which is about 11 kilometers, is the threshold where our alignment test return a p-value of 0.005. The p-value is a statistical parameter which is like a measurement which gives a meaning in terms of is the grid aligned or not. That means if you randomly rotated this grid 1,000 times and optimize each one, only 5 out of those 1,000 trials would match what you see here. So 155 of our 160 sites, nearly 97%, fall within this distance of an E8H. Well, you can see here I've got Google Earth presenting those ages, and the circuit sites, there's 160 with green marks saying this is close to those ages within 11 kilometers, which is very close on the planetary scale. And now I'm going to present you a second layer, which is a layer of share ages. And there are only 19 ages of the 367. Now I'm filtering down to just the ages that connect 2 or more sites simultaneously. These 19 ages are the most compelling features. They are the ley lines, if you will. Notice the patterns. There are 3 separate ages linking Uluru in Australia and Kata Tjuta in Central Australia. So they're very close, obviously. But we can count 3 ages. So these lines thicker. Those thicker lines are the share ages between simultaneous sites, okay? And then if we go to the Easter Island, there is a trail of sites as well there. So if I can find that, there's Rano Aroi, That's it, they are green. So Easter Islands, Rano Aroi and Rano Koi. So if I go to those, they also share ages from a single E8 vertex. Well, 3 ages, as you can see. So these triangles are actually vertices of the grid of the EA lattice. So they are anchor points where the edges can be drawn. And obviously, when we draw those lines, the sites which are closest to those edges within 11 kilometers are shown here. We have also the Great Pyramid of Giza and the Mount Olives in Jerusalem, sharing an edge where the Giza endpoint is just 9 kilometers away. So let's see that as well. There's all the rest. As you can see, they are marked red because they've been filtered. Filtered from single age to share ages between simultaneous sites. Minimum 2. Okay, so we've got here Great Pyramid of Giza and the Mount Olives in Jerusalem. So if I click on Great Pyramid of Giza, you can see it's at 1.1 kilometers. It's not a lot. It's very close. So if I can zoom in, we can see how close it is. So we've got the Great Pyramids. So it's not 9. Well, it's not 9 kilometers away. It's actually 1.1 kilometers away. For that particular share edge, okay. So these are not coincidences we weren't looking for. They emerge from a single mathematical optimization across all 160 sites at once. This is a lot of mathematics behind the scene. And now I'm going to show you another layer, the third one and the last one. We are going to look at the full amount of ages of that E8 lattice structure. And there is in total of 6,720 ages. As you can see, it's like a web. And it's very difficult to see what's going on. So that's why I had to filter it and highlight the meaningful ages we are looking for. We are looking for a meaningful alignment. So for full transparency, there are 5 sites out of 160 which forward side are 11 kilometer threshold when measured against all of them, 6,720. So we're looking at the bigger picture here. We've zoomed in, and now we zoom out. So, which are the 5 outliers? So there are, and because I've asked to render, to render the sites in the outliers as medium threshold within like 15.2 kilometers, they're like yellow, orange, and over this red, but there is none here because I limited to 15.2 for medium threshold. So we've got Terra de Jesus, High Tatra, in Slovakia. High Tatra in Slovakia is at 11.7 kilometers. And then we have Niagara Falls, also at 11.7 kilometers. We've got Mount Elbrus in the Caucasus at 12.2 kilometers. We have Pritz Bay in Antarctica at 13.3 kilometers. And Terreiro de Jesus in Brazil is the furthest. The furthest are just 15.1 kilometers. So that's the furthest among all the 160 sites. And on a planetary scale, it's not too bad. It's not too bad. So we are looking at a very meaningful alignment of projections of an 8-dimensional structure, a subset in 3 dimensions on the Earth's surface. So to put that in perspective, that's the distance of a short drive, okay? These 5 outliers are scattered across different continents with no pattern, which is exactly what you would expect from a genuine alignment or geometric fit. With a small number of random misses rather than a systematic failure. And obviously, for this type of work, I'm not cherry picking. I'm not actually trying to find an alignment through visual and trying to connect because it looks aligned visually. I'm actually letting the statistics speak by themselves and show me the alignment, which is different approach, the rigorous mathematics behind strong, solid. So when we talk about the ley lines, we have to make sure they can actually beat chance or randomness, particularly when we rotate the Earth. Else, if it can be found by chance, if it can be found by random rotations of the Earth, then they're not meaningful. That's what I'm looking at. We have to look at something quite unique, but they're not particularly. There's not like global network, if you want. I mean, they are particularly significant in a band or a range of within a threshold of kilometers, like here 11. Then beyond that, if we look further, then the signal is lost. Okay, so it's about quantifying meaningful results in mathematics, which statistically will leave no doubt that there is meaningful alignments between those edges, or ley line, if you will, and the circuit sites. So I could look at different data sets. Here is an example, 160 sites, and they are the sites I've actually choose from a researcher well known in circuit sites or ley lines is Robert Kuhn. I actually choose a data set of 156 sites of his plus 4. So I added it all, it's 160. And that has shown that there is a potential meaningful network, but it's not, we can't tell there is a unique, with the EA lattice, which is a high dimensional structure, we can't tell there is only one unique network, global network connecting the sites. It's actually not true. It's actually, we are in a territory where the structure of the high dimensional structure, the structure of the high dimensional geometric set like the lattice is rich in space, and we are exploring different angles and different way to see it. And I believe because only now we haven't understood fully how the E8 structure works, and I think with this type of work we will see a bit, but not the full picture. We'll see a bit, but it will require a lot of research, deep research, to actually have a full picture of how the E8 lattice behaves across the planets, and how we can interpret it meaningfully with the data set we work with, either circuit sites or geophysical data sets, tectonic plates, and so on, volcanoes. So there is many data sets we could work with. But this is a good start with 160 sites, and I'm very glad I found a meaningful alignment within a threshold. So that was through an analysis of 20 subset of the lattice, and only one survived, is that particular subset I'm showing you. All the 20 subset I analyzed had shown all the 90 others. The 90 others haven't shown any significant signal, and so now I'm running another set of 20 seeds, or 20 E8 subsets, between 20 and 49. So I've done 0 to 19, and now I'm doing 20 to 49, and I'm going to analyze those and see if I can find any another E8 lattice, an interesting E8 lattice subset, which has an equivalent alignment like this one. Maybe more, it can be more powerful or less. The E8 lattice is very rich. There's so many we could discover. There's thousands and thousands seeds we have to analyze, and more than that, millions. There's millions of E8 subsets in 3 dimensions from an 8-dimensional structure. So that's what I mean. And this E8 lattice definitely outperforms the platonic solids. Okay, it outperforms any grid we've ever known now. It outperforms Goldberg. It outperforms geodesic grid as well. So, and because it's a rich and dense structure, there's no doubt if we work with higher dimensional structure, we will find more significant results and find more information about the planetary grids. It's not just a 3-dimensional structure. Unfortunately, if we want to go further with the ley lines, we have to study the higher dimensional structure and not just the 3-dimensional structure. So that's what I'm doing. So yeah, so that was my first presentation on the planetary grid, and if I find any more meaningful E8 lattice, then I will present it for the next couple of videos. Or I haven't actually studied any other geometry shapes except the E8 lattice. I'm still on it. There's so much to discover with this one only. But I could work with other higher dimensional structure, because I've gone out the mathematical pipeline. I could implement it and see as well other higher dimensional structure. But I will go slow. I'm trying to understand the first one, the E8 lattice, which is the most obviously significant structure in mathematics and physics. to do with obviously the string theories and all sorts. High, very theoretical models that use very high advanced mathematics theories to do with this string theories and all sorts. But I haven't been going to the directions very much. It's only now I have actually explored the lattice by trying to understand the planetary grid and have some meaningful results, but also statistically have concrete and solid results, and not just cherry picking and saying this is an alignment because I can see it. Visual can be misleading, can mislead easily. So, but the maths, when you've got very strong solidity in maths and you present those results cleanly, then that's fine. I mean, there's no doubt you're onto something. Right, so I'll leave you for now to digest this, and I'll see you soon for another presentation. Thank you very much, and see you soon.